COVID. For COVID.
Yes. Play. There we are. IPC. Yeah, a little bit dirty. So that's where we are going to get started. A very exciting one, and we will spend the rest of the session talking about IPC. So we learned process. Okay. We learned threads, and in fact, there are a couple of review slides, and I always like to show these slides, as you can see on your screen, to help you to recapitulate, to remember all the important things that we passed through in those two sections. Process, we learned process model and multi-programming that involves quantum of time, context switching, and PCB. Now, the scheduling algorithm we didn't study. We will study it in the next part after IPC. Then we have PCBs, then we have CPU utilization, and here's the CPU utilization. Then finally, we also studied threads, and some of the key things that we learned here is right in front of you. Okay. Then inter-process communication. In the inter-process communication, this is what we are going to study. Now I will start the presentation. That's what we are going to study. That's what we are going to study. Race condition, critical region, mutual exclusion with BC weighting, and lots of others. So the couple of things right to get started with, because I already gave you the overview, the context of why we need it, and what are the things we are essentially expecting from this particular chapter, right? We already talked about those things. So straight away, we jump into race condition. Yes, you heard it right. It's a race condition. Now, what exactly is race condition? When we were talking about threads, I think I mentioned it with an example, because in the case of threads, we share data and share resources. Since we share data and share resources, there's a chance of overlapping, because we already know that when it comes to sharing some resources, sharing data, especially where there is a dependency present, that's the word, that's the key word. Race condition doesn't really happen unless there's a dependency. So there are two conditions that must satisfy. The two conditions that must satisfy for a process or a thread to run into race condition. The first condition is there must be a shared data involved or shared resource. In fact, data itself is a resource. So we will just use the word resource. A shared resource. Number two, there must be a dependency between two programs that are sharing the data or trying to share the data. Do you get the point? So there must be two reasons, two conditions that must satisfy for a race condition to happen. Clear? So let's move in and see what we are having. There exactly we are talking about race condition and talking about dependencies. Talking about race condition and talking about dependencies. Yes, There needs to be a dependency. And there's an example that they have given. You can quickly read through it. It's pretty easy to understand. Let's suppose there are two programs. The first one is a program that generates a value, a particular value, and the second one is the one that prints the value. Okay. So the second one is supposed to run after the first one has finished, after the first one has finished its run. Right. The first one has finished its run. So that's what we call dependence. There must be a dependence. Now the point is, as to say, the proper sequencing is required. That's it. If you don't sequence them properly, if you don't synchronize, let me use the word synchronize, we will find that word very soon. Synchronization. Unless you synchronize these two processes properly, there's a fair bit of chance that they will overlap each other, right? What I mean, just imagine that process A, which is supposed to generate, say, for example, the value, a new and updated value of a variable called X, and then X is supposed to get printed to a program B. So basically, A will be X, the value of X, the updated value of X is supposed to get passed from program A to program B, and then B, who is supposed to send it to the printer. If there's a dependency like that, and for some reason they just overlap. For example, before process A could actually finish the calculation or getting the new value of X, maybe process B started running. So what do we get? Will we get a deadlock? No. Race condition never makes a deadlock. So we'll definitely, something will go, some sort of a value of X will go to the printer or will get printed out. But what we will get is not what we expect. That could be an old value of X, not the latest update sent from process A. So that is what we call race condition, where dependencies are available for a shared data, dependencies are present for a shared data, and there's no choice. We have to enforce proper sequencing or synchronization. If in case we can't do that, then what happens? Then there will be a race condition. As you can see on your slide now, this, by definition, is what we call race condition. So the point is there will be lots of long, complex sentences like these ones, okay, in your book, in your textbook, and also in your study materials. That means the slides. But try to understand the core concept. Not necessarily you have to remember or you have to memorize those definitions or something. No need, absolutely no need. But yes, there are keywords, and I've tried my best in these slides, you can see, to highlight the keywords and expressions. If you can remember those keywords, then probably you can answer these questions easily. You can construct your own knowledge base and your idea. Now, what happens? As I said, if race condition happens, we are not going to run into a deadlock. Deadlock means the process will stop. The process stops in the middle of operation because it doesn't know how to run to completion, okay, or simply how to release the resource. And from the resource point of view, it gets blocked for an indefinite period of time. So race condition will not create any of those situations. Race condition, in race condition, the process will run to completion and release the resource. But the final output, or if we are considering a resource, we might say the final state of the resource, as you can see at the bottom of the slide, will become inconsistent, unpredictable, and hence pretty unstable, which is not a welcome thing, definitely not a welcome thing. So a stable resource becomes unstable because of the race condition that leaves it in an inconsistent and unpredictable state. Clear? Now the big question is, what can we do to avoid it? Well, before we jump in there, we will talk a little bit about critical section. What is a critical region? There's a one that you'll be using quite a lot. What is a critical region? A critical region, well, right from the beginning, I must say that critical region can be looked at or can be explained from two different perspectives. The basic thing is still the same, but these are all different perspectives. One from the perspective of the resource, and one from the perspective of a process. So let's just try to understand or look at it from the perspective of a process. So a process, just assume it's a single-threaded process. A process is nothing but sequential execution of code. So say for line 1, line 2, line 3. Okay. Now for a simplified understanding, let's think that's the way your process is running and getting executed. Line by line. 1, 2, 3, 4, 5. And now on line 4, probably, you have written an instruction that is trying to acquire the printer to send something to print. Okay? If that is the case, then you are actually running into a critical section. That piece of code, that part of your program will be called critical. That part of the code is what we call the critical section of the program. Did you get my point? So if you're looking at it, because in many places you will see they talk about the process is working at the moment, it's running in its critical region. What does it mean? The bunch of codes that tries to access a shared resource will be considered, that bunch of code will be considered the critical region, right? That is, so what does it mean? It means that two processes running in their critical region, say for example, is another process which also wants to acquire the same printer, but these two programs shouldn't try to access the printer at the same point of time. In other words, these two processes shouldn't be in their critical region at the same point of time. Okay, that is what we mean. That this becomes one of the conditions. You can see I have just made the slide. This is one of the conditions that I have mentioned right here. The first, the ones that I have highlighted with blue color, they're very, very, very important. They're indeed very important, and you are supposed to remember these four conditions, and these are the four conditions. Again, we will be talking about these four conditions later when we go to chapter 6. Okay, in a slightly different context, but that's it. So now that we have these ones, the very first one that you can see right there, the very first one that you can see tells us about that there we are, right from the beginning. So we understand critical region from a process point of view. Now, let's finish the thing that we were talking about, the perspectives. Now, how about from the resource point of view? The best way to understand from the resource point of view, in fact, whenever you are using a shared resource, you are most likely trying to enter a critical region. Okay? Any shared resource. Now, there's an interesting point. When we talk about shared resource, please remember that the resource is shared, but that doesn't mean that multiple programs or multiple processes can use the resource at the same time. That means they can take turn on that particular resource. The classic example for this is the ATM, the machine where you go there, the automatic teller machine. All of us, we go there. So basically, it is a shared resource, isn't it? Because all of us, we can share the benefits that this particular machine offers. But we must take turn on that ATM. This machine is not designed to serve two customers at the same point of time. If it happens that you and me together, well, we can stand in front of the machine together, no problem, but we are not allowed to put our cards, our ATM cards, into that slot, that card slot, at the same point of time. If even by mistake, intentionally or unintentionally, we do it or we try to do it, the machine will be deadlocked forever. So, from the resource point of view, that is the critical region. So now we understand what the critical region is from the resource point of view. You can say it's up to your interpretation. If you say it's all about, you say the ATM machine itself is a critical region. Yes, probably you're right. Or some of you may zoom in and say, no, it's exactly that card slot where you are supposed to push your card in, insert your card. That itself is the critical region. That's also true, in whichever way you look at it. Now that we understand critical region, let's look at these four important conditions that say it's important to avoid a deadlock. Okay, what is that? First, no two processes should be in their critical region at the same point of time. I think we already explained it, right? Now we move on to the next one. What's the next one? No assumptions should be made about the speed of the CPU or the number of CPUs. Of course, number of CPUs, if there are two processors, then speed will be higher. Okay, so speed of the CPU. That's true because CPU itself is just another piece of hardware. And just like most of the hardware, well, all the hardware, it is a mechanical device. Okay, and for a mechanical device, it's best not to make an algorithmic assumption about what could be the speed of that particular mechanical device every single time you run that device. There's no guarantee that every time it will it will always take the same time. There's no guarantee for that. So we shouldn't do it, because if you do it, and if you write an algorithm based on that assumption, so you're asking for trouble. What sort of trouble? Because when you eventually you send a process right there, and the process goes there and acquires that resource, and then it finds that it's just a fraction too early, because the process which was using the resource before him, before it, is still there, and there will be a deadlock. So we need to be careful from that. Number 3, no process running outside its critical region should try to block another process. That is also important. So there shouldn't be any blocking, because if the block, basically who suffers? Everyone suffers. All the other processes standing in the queue will be suffering, because no one can do anything on that particular critical resource. Okay? And at the same time, the resource itself is lying unused. The resource is lying unused. So this is one of the problems that we must deal with. So that is exactly what happens. Number 4. Number 4 is no process will have to wait for an indefinite period of time to enter its critical region. In technical terms, we call this condition starvation. So no process will have to starve forever. Okay. And why it happens? Well, it happens because of priority or prioritization. In fact, the priority or the prioritization So what happens with the prioritization? The prioritization is where a particular process is given higher priorities. But why do they give higher priorities? And in fact, later we will see in the later part that we do have algorithms to prioritize this. So why do we prioritize the processes? Because it's obvious all processes inside your computer are not of same priority level. There are some processes which are more important than the other processes, and hence we introduce this priority-based algorithm. Okay. This priority-based algorithm to prioritize some of the processes. The next one is, if you obviously you understand that when you prioritize some of the processes, you are actually asking for starvation. So what will happen to the low priority processes? A situation may arise where the low priority processes will suffer forever because they simply never get a chance to go to the CPU. Okay. So that is a condition that must be avoided at any cost. Okay. If you think about an analogy from the ATM point of view, it will be the same thing, because on the ATM machine, these are the obvious things that we face. Right? First of all, two of us, we can't do transactions in ATM. Number 2, sometimes you go to an ATM with an assumption that within the next 5 minutes, it could be your turn. But that never happens, because the guy in front of you could be withdrawing 100 million dollars. So maybe you have to wait. Okay. in your position on the line for the next 1 hour. So don't make any assumption. Number three, there shouldn't be any blocking, because if two guys that can't take a decision who came first and they start fighting, it's a wastage of the ATM time, because the ATM machine, the ATM is lying idle. The machine, no one is using that machine. And at the same time, these processes are trying to block each other. This is an analogy for those who want to remember these four conditions. And finally, the starvation. It happens. You are there standing in the queue under the sun, and suddenly someone comes there, a very important customer, a privileged customer of the bank, and the security will just shove you off. Okay. You get out of the line. This guy is a VIP customer, will always get the first access to the ATM. He doesn't have to wait under the sun or stand in the queue. That's the special privilege the bank has given him, since he's one of the most important customers and the big investors, one of the big investors in that bank. So it is, if you put it analogically, you can actually remember these things. These things are not difficult to understand. We have to remember these four conditions. Okay. Now we talk about mutual exclusion. In fact, this is the same thing that we were talking about in the last slide, and the first condition where we said that no two processes can be simultaneously inside the critical region. Okay? And that is what we mean by mutual exclusion. So if one process is in, the other process must wait for their turn. Now, what is busy waiting? Well, mutual exclusion, most of the time, when you enforce mutual exclusion, or when we think about mutual exclusion, one of the biggest problems that we have to deal with, of course, in terms of IPC, as I said, we have to enforce and ensure mutual exclusion. And that's why you are looking at all these things. As you can see, in fact, they say the proposals for achieving mutual exclusion. And these are the things that we are going to study in this section, ending up with Semaphore and Mutex. Okay, so that is what we are going to study in this particular section. But mutual exclusion in general can give rise to busy waiting. Okay, we will talk about it in a minute, because it is, as you can see, one of the names there. It can give rise to strict alteration. Whenever there is a strict alteration, it ends up that most of the processes will end up doing a little bit of unwanted busy waiting. Okay. So we will see it in a minute. So we now understand what mutual exclusion is. Now, here's a slide to show you what race condition is all about, for an analogy. Now, process A and process B, and you see the person A and person B. Okay. Now, if Mr. B could start checking the refrigerator a little later, then probably they wouldn't have ended up with too much milk. Just because it overlapped, they ended up with too much milk in the refrigerator. Again, the final state of the resource becomes unstable, unpredictable, and inconsistent. That's not welcome. So what can we do to resolve this issue? Remember what we said in the first slide? We said proper sequencing when dependencies are present. And what we mean by proper sequencing, and the technique that we use, you have to remember this word, technique that we use to address the issue of race conditions is synchronization. As you can see at the bottom, you have to remember this is the technique. In fact, those who will learn Java, multi-threading in Java, you will find a keyword in Java. It's like in Java, yeah, they have a lot of keywords. They serve different purposes. They are part of Java's intrinsic programming environment. We will find a keyword called synchronized. So they must be synchronized. And it is important that they get synchronized. So synchronization is a technique that is used to ensure mutual exclusion or proper sequencing. Okay. So the first thing we will go on to check is this one. Remember, from now on, whatever we are going to talk about, we have only one purpose in mind. If you are in, I must be out. Proper sequencing. Proper sequencing. Okay? So that is what we called mutual exclusion. So the first thing that we find there is disabling interrupt. So a process acquires a resource. A process acquires a resource, and immediately after acquiring it, it disables all the functions by which this resource would actually give an interrupt. So basically, it takes the resource, it does something to take the resource off the radar. It takes the resource off the radar. So that is what it does. Off the radar means now it can't generate an interrupt. And as we understand that any hardware resource that wants to communicate with the kernel or the OS, okay, or in fact the system, must do it through interrupts. But if you disable interrupts, that means no one can get in touch with this resource, and this resource cannot communicate with the system. Now, the process will do it as long as it is using it. When it finishes its task, it will again re-enable all the interrupts and simply walk out of the resource. The second process will come there and will do the same. Now, this is fine. If you can imagine this situation, that you can say that, oh, all right, so that's the way to ensure that they are mutually excluded. So when he is inside, when one process is inside that resource, no one can actually disturb him. But there is a problem. And what's the problem? The problem is if something happens to that particular process while it was still using that resource, for example, for some bad codes, it collapses. It simply dies. And there's no way anyone can wake it up. You get my point? So that could be a catastrophic deadlock, isn't it? So that is the problem that we are thinking about. Now, if you think you want to remember it analogically, again, just think of it that you had a long flight, overnight flight, and you checked into your hotel and you just want to sleep for the next 5 or 6 hours. You checked into your room and you locked yourself up and you disabled all the possible sources of interruption. For example, you hang a door card, say, don't disturb, and then you disable the doorbell, then disconnected the telephone line. So all possible interrupts that could actually disturb you while you were enjoying your sleep inside your private space have been disabled, and you now go to bed to take rest. But in case, and you are supposed to wake up after 5 hours and enable all the interrupts and reconnect the telephone line, enable the doorbell, remove the door card, open the door, and step out. But the problem is, at the time when you are asleep, if something happens, something bad happens to you, okay, could be a heart attack, could be whatever, a serious medical condition arises, there's no way, no one will get to know exactly what has happened to you. And they will still start thinking, they keep thinking that you are, as a process, still busy doing your task inside the resource, inside the room. But in fact, something else has happened. So that is, analogically, this is the challenge that you'll have to deal with if you go ahead and implement disabling interrupt technique. So disabling interrupt is a good way, sure, to implement mutual exclusion, but there's a drawback. So we move on from there. Move on to what we call lock variables. And as we say lock variables, locks are binary locks. You can have two values, zeros and ones. One for lock, one for unlock. So in this concept, we assume that a resource, there's a process will now step into the resource, and the first thing it will do will put a lock there. The moment it will go there first to acquire that resource, it will check the lock. Any resource will now be associated with either of these two locks. At any point of time, it has its lock on or lock off. To understand it in a better way, or to put in the right perspective, think about your experience everywhere, all around you, when you encounter the green light and the red light. Green means on. For example, you're traveling in a train or you're traveling on a plane and you want to go to the toilet, you go to the toilet and you see there's a red light. All right, the red light on. The red light on means the toilet is now being used by another process. So what he did after stepping into the toilet, he switched on the red light. It's actually automatic, and the red light is switched on. So that means that this resource is now off. So what you do, well, it's up to you. If you want to wait there, you can stand outside and waiting for the light to turn green. Or if you want, you can just take a walk and go back to your seat and then come back and try your luck once more 5 minutes later. Well, try your luck once more. Okay. That means that when you come back after 5 minutes, you might still see it is red, but that doesn't necessarily mean the earlier guy is still using it. Probably he left, and during these 5 minutes, another guy has taken it. So there is no choice for you. But we must take turns. And that is all about mutual exclusion. So yes, this sounds a little better than disabling interrupts. Okay? But still, so what log variable is log variable gives you the strict alteration, the red or green, as I said, that when you go there and you see the red light, you either wait, and that's what most of us do, or you just go back to your seat and try your luck 5 minutes later. There's no guarantee, even 5 minutes later, it will turn green. It's all up to your luck. Or even if you're waiting, how long you will have to wait for the red light to turn green, you just never know. So think about a situation like this. In the morning, you left for local ATM and told your mom that I'm going to get some money and I'll be back in 15 minutes. Okay. Now, more than half an hour has passed, nearly an hour has passed, and you haven't come back yet. So your mom gives you a call and asks you, son, where are you? What are you doing? You answer her that I'm busy. And she says, you're busy? Busy at what? And you say, I'm busy waiting for my turn. Try to think about it. I'm busy waiting for my turn on the ATM, the resource. And that's exactly the situation that arises from strict alteration. Did you get my point? If you implement lock variables, the green and red light concept, this is probably the problem that you're going to run into. It's not a problem for the others, but for most of them, everyone will have to wait for an indefinite period of time, like uh, wishing that they are a little bit lucky that the guy or the process which is currently using that particular resource will step out very soon. At least their chance will come. So basically, they don't know for how long they will have to wait. And while they are waiting to acquire a resource, their performance is going down because they are kind of paralyzed. I mean, in terms of processes, they could have done some other important things and come back. Okay. So that is what you are looking at in this slide. The bottom few lines, you can see the first thing that we are talking about is busy waiting. So remember, strict alteration gives rise to busy waiting. Strict alteration gives rise to busy waiting. Right? So what can we do? Now, the next solution that we have is Peterson solution. This is probably the first time that they try to combine a few things, taking turn and strict alteration. These two the concepts were combined together, and for the first time in Peterson's solution, they were hinting at something a little bit different. And if you go through these pseudocodes, these are all pseudocodes that you can see, there are certain words there that certain expressions that is actually hinting at something different. What is that difference? To understand it, we have to go and study the technique itself. And we move on to the next slide. That is TSL. That is TSL. Test and set lock. Very, very important concept. Very important concept from your exam's point of view. So what is a TSL? TSL, in the TSL concept, it was actually proposed in Peterson's solution, and then it was implemented towards end in a more sophisticated way. Of course, we'll see it in a minute. But let's try to understand what's happening with the TSL. TSL is all about the threshold, or the doormat, as we call it. Just imagine there's a room there and one door, and that room is a resource. Whoever steps into that room will close the door and start using it. So in other words, only one person is allowed to use that particular room at any given point of time. Right? And then there's a doormat in front of the door, just outside of the door. It is the doormat that we are paying attention to at the moment. Because up to this point, we were talking about mutual exclusion. We're trying to get it or enforce it on the resource itself, because the resource is the critical region. But now we shift our focus. Yes, that is mandatory. And we shift our focus and we understand that to ensure that mutual exclusion persists, can be enforced inside that particular resource, we have to guarantee that there's no busy waiting for all the processes that wants to acquire that resource, and that the processes which have already been allocated that resource by kernel. I think I mentioned it in my overview in the last session. It's all about a game of allocation and acquisition, resource allocation and resource acquisition. So multiple processes, they are asking for the same resource whenever they send a request to the kernel. The kernel logically assigns that resource to that particular process. So all process has been allocated their share of resources. But allocation doesn't mean acquisition. Acquisition is when that process goes there to acquire it. And that is where the conflict comes. And that's why we are here in IPC. That's why we are talking about mutual exclusion. So TSL is important because it takes care of these two regions, as you can see right there. Enter region and leave region. I call them the doormats or the threshold. So not only we have to ensure that mutual exclusion proceeds inside of the critical region or on the critical region, but immediately outside of the critical region, there too must be a mutual exclusion. In other words, those who are supposed to step into that particular resource after this current guy has finished his task, only one of those guys can stand on the threshold of the doormat. No two guys will be allowed to stand there. The other guys do not have to worry, don't have to wait, because it's not their turn. The next turn is not theirs. So they will just walk around and do whatever they do. And when their turn comes, they will be alerted. How will they be alerted? And this is the mechanism that we are going to talk about. The slip and wake up call. The two calls that will help you to implement TSL is what we call slip and wake up calls. Okay. What are these sleep and wake up calls? You can see right here. They're going to show you sleep and wake up calls. The first, we try to implement this TSL technique, a very quite oversimplified logic, and that is the one we called sleep and wake up call. So sleep call and wake up call, what does it mean? Sleep call is a system call. Try to understand. Sleep is a system call. Who gives the sleep call? The process which is currently executing inside the CPU, inside the resource. Any resource. The CPU is just another resource. Will give itself, is a self call, will give itself a slip call, or simply it will give a system call to the kernel, asking him to block himself on CPU. So it's a self call, it's a system call, and sole purpose is to block itself because it has already finished its task. Wake up call. Wake-up call, on the other hand, is a broadcast call. What is a broadcast call? A broadcast call is not for the same process. A broadcast call is a public call and it has one parameter. And what is that parameter? That parameter is one particular process which is currently in the ready queue. So how does it work? Say, for example, P1. P1, or process 1, is about to acquire that critical resource, or step into that critical resource. The moment it steps in, the first thing it does is to give a wake-up call, a broadcast call. For whom? For, as I said, one of the processes, only one of the processes which are waiting, who are waiting in the ready queue. And what does these wake-up call mean? Well, this means that he's basically selecting. Before entering his own critical region, he is selecting the next guy and asking him to get ready and come over here and wait on the doormat, the enter region. The others don't have to worry. You don't have to wait. You just go ahead, do whatever you want to do. Don't waste your time, but just stay alert that whenever your name is broadcasted, you will be the next one. So you'll have to move from the ready queue to the doormat. Stay prepared to step into the critical region. So that is how we ensure, as we say, that mutual exclusion is also implemented not only on the critical resource, but just outside of the critical resource. And that is the key. That is how it all works. Okay? So that is what we call sleep and wake up call. They're talking about a violation, so we'll just try to highlight the important things. That can happen with sleep and wake up call because you need to know that there's some priority inversion. Because as I said, right, some processes are highly prioritized. So whenever they come, they will always have the first preference to go to the CPU. They will always have first preference to go to the CPU. So that is the problem. That can create a problem if you follow these algorithm of strictly implementing these sleep and wake up call. So there could be a priority violation. That's what they're talking about. So what is the solution then? Well, they've given an example to understand that how it works. A sleep and wake up call, and they have mentioned what sleep and wake up call is all about, and we already talked about it. They've given a classic example. This is in fact a classic example, not only here, in some other parts where you have a similar discussion, you will be finding this example. It's called the consumer and producer problem. Just assume that consumer and producer, okay, these are two processes. These are two processes. And the buffer that they are talking about, the store where they're supposed to be active, both of them, is a shared resource. And in principle, only one guy can work there. Both producer and the consumer can't be active inside the store at the same point of time. So they can't be active inside their store at the same point of time. So that is one of the things that we have to understand. Now let's see what happens. So the producer, initially it's empty. The buffer, the store was empty. Producer produces the first item. And as he produces the first item, so that means this process producer steps into the critical region. As he steps in, the first thing he does is to give a wake-up call to select the next guy. In this case, it will be the customer, the consumer. Okay. So consumer will now get ready. In fact, now consumer will move from the ready queue to the threshold or the doormat. And if there are multiple consumers, you can imagine that this call will go to a particular consumer who is going to be the first one to step into the store when producer has finished putting his items on the blocks. So that is how we implement this mutual exclusion at two levels. The first, not in the critical region, but also in just outside the critical region. So then, as you can see, the producer goes on to fill it up. And finally, the consumer takes the first one out. And as the consumer takes the first one out, he gives a wake-up call to the producer. A wake-up call doesn't mean that particular process will have to jump in immediately. But it does mean stay prepared, you will be the next one. Clear? So now that we understand this one, here is something, a very important, a few things that you can see at the bottom of the slide. We do ask questions from this part, so pay attention. It's a very common question, it's a typical question. What are the conditions? The sleeping conditions and wake-up conditions. Okay. For producer, buffer full. For consumer, buffer empty. Wake-up conditions. For producer, there's space in the buffer, and for consumer, there are messages in the buffer. But when we try to implement this technique, we have noticed a problem there. There could still sometimes be a little bit of overlap. And that is what we want to avoid at any cost. So what can we do and how can we do? There's still problems. Because remember, we need absolute mutual exclusion. Absolute. We don't want to take chance on anything. So to ensure that there's literally no possibility of overlap at any stage for whatever reason, because the question is the live region. We said that normally speaking, in the sleep and wake up call, the process which is currently using the critical resource is supposed to give a sleep call on itself. And only after kernel has blocked it, then we do expect that this threshold guy or the doormat guy is supposed to step in. Now there needs to be a synchronization. If there's even a slight bit of overlap, because remember, we are involving a little bit of hardware here, CPU here. CPU is involved because CPU needs to be taken back. And again, CPU needs to be assigned to that new process which is going to use this particular resource next. So a little bit of hardware is involved. And as we said, that no assumption should be made about the speed of the hardware. Okay. So there could be a chance of an overlap. To address this issue, we move on to our final solution that we called mute semaphore. Please remember this one and do your own research. In fact, you'll see lots of different implementations. Even sometimes the people are on the internet, you can see how to write the programs to implement semaphore. You don't have to go that far, but conceptually, you must be clear what semaphore is. Semaphore is literally a signaling system. Semaphore has two states, up, which basically comes from the wake-up call, and down, which basically gives a sleep call. So semaphore has three states. The two states are up and down, and the third state is what we call mutex, which literally means mutual exclusion. And what is it? It is a lock. Mutex is the state where a process will acquire a lock from the kernel and return the same lock back to the kernel. Okay, so that is what we do. Okay, now why we involve the kernel? We involve the kernel simply because that if a lock is involved, then the kernel is the sole manager, the resource manager, then we can guarantee that mutual exclusion will persist. That is the reason that we use or we ask kernel to get involved. Okay. So that is all about mutex. Mutex, remember, mutex is a state in the semaphore, but which basically refers to a lock. And this lock comes from the kernel. And there are certain things that we can do with the lock and certain things that we can't do with the lock. For example, once a process has acquired this lock, it can't, no other process can snatch it. They will have to wait until that lock has been removed. So what happens now is a resource try to understand it in a visual way. What happens now is, think about it. This is the critical region. This was the critical region, and this is the enter region. Okay, and this is the leave region. This is the enter region. This is the critical region, and this is the leave region. In fact, enter region, leave region on the same side and the same thing. It's just an imaginary zone, just visualization for our understanding. So a process, a P1, is right in here. So when P1 steps in, it gives a signal which is called semaphore up, which is basically a wake-up call. And we already know what wake-up is. Waking up one of the other processes from the ready queue and moving it to this enter region or the doormat or the threshold. Okay, so this will now move right in here. And as P1 enters this critical region, it sets the lock or the mutex lock. The mutex is now locked because it is busy working on that resource. This process will have to wait. So not the other processes, we don't have to wait for mutex. Because since it's the next guy already selected, so this guy will have to wait. So one guy is waiting for the mutex. It's not that 5 guys jumping on kernel to get the lock. No problem. And no one can disturb P1. So P1 finishes its execution and comes back. Now it is time for it to leave the critical region. So what P1 will do, what P1 will do is will move itself to this leave region. As it goes to the leave region, it gives a down. That means a sleep call. And sleep call to whom? Sleep call basically means asking kernel to block itself. And when it is blocked, this is where there is no chance of overlapping. It will set, and by giving a call, it will turn the mutex on lock. Since mutex is a key and that has been unlocked, then this guy, the new guy, will pick it up or go there and set its own lock. So only one process can set its lock on this mutex. And that's how it controls these operations. And that's what happens. So basically we ask, what is a semaphore? What is a semaphore? What is a semaphore? And semaphore is a signaling system. Semaphore is a signaling system. And this one, the mutex, is a locking mechanism. So these two things work together to ensure mutual exclusion is enforced. So that is essentially what they do.
Upside down. Upside.
So that is exactly what they do. So we have come to the conclusion, basically, and as you can see right here, the mutex lock and mutex lock unlock. Mutex lock is called when a thread needs access to a critical region, and mutex unlock is called when the critical region is finished. And it must get blocked. Okay? And it must give a wake-up call, and it must get blocked. So that is exactly how these things are working together. Right? And that's the way we ensure absolute mutual exclusion at the IPC level. Right? Whenever we talk about IPC, we think about mutual exclusion, but with no busy waiting. And the way we achieve this implementation is by using a variable called semaphore, which has 3 states. Semaphore up is basically wake up. Semaphore down, which is basically slip, and a lock. And the state of the lock can be either locked or unlocked. Depending on that, that state of the lock will be reflected in the third state called mutex. Clear? That's the story that we have so far in mutual exclusion. Up to this point, if any of you have any question or any part that you didn't understand, we need to rediscuss, let me know. Because after this one, we will talk about 2 or 3 more things, basically the ways of implementing or ensuring mutual exclusion. But most of it, they are more relevant to distributed applications, distributed resources. So up to this point, if you have any question, you can ask me. The most important thing is the TSL and its final implementation through semaphore, up, down, and mutex. Mutex is a state. As we said, there are 3 different states. And mutex involves acquiring a lock and releasing a lock, which only one process can do it. And we already know, because by using the up call, up state, or the wake-up call, we have already chosen the guy who is supposed to be the next one to set the lock. We acquire the lock from the kernel. It's a kernel level lock. If you have questions, you can ask me. Or let's move on to take a quick look at the other things. A few other options. This is the Mutex Monitor. It was introduced back in 1973. It basically is more like running a small program. Well, you can think about, programmatically, you can think about running an if condition before you try to enter the critical region. Okay? Or in Java, as we do, if you have learned Java already, you know it, try and catch. Okay? In Java, we do the try and catch. So in Java, that's what we do. Because every time a process wants to access a resource, a shared resource, it will always run that program. And it can be, it is, in fact, this monitor is a program that is in the hand of the programmer. The programmers can write that particular type of program to ensure that the critical region is checked before a process is allowed to step in. So just look at this picture. The red block is the monitor program. Okay. And if another process wants to step in, it will check. And as I said, it programmatically, it looks very similar to if, else, or in case of Java, try and catch. Another one that we have is message passing. Okay, how do we pass the messages? How do we pass the messages? That is one thing by constantly passing and interchanging messages, the IPC is also conducted using system calls like Semaphore to primitives, send and receive. Okay. That was another mechanism, but that is more common when there a communication or an IPC is happening over a network. That is more common. It's happening over a network. Okay, as you can see. But here, acknowledgement is something that we are always looking for. Okay, acknowledgement is the key issue. Then finally, we have barriers. What is a barrier? A barrier too is the large distributed type of programs, and which basically means that you run the program and all the programs must reach a point where they can get started once more. Okay, so basically we start the program and then we start multiple programs, and these multiple programs will keep moving, keep executing. They will take their turns. Okay. And after taking turns, they will come to a point where they are actually at different level of completion. But that's what we don't want them to be in. I mean, honestly, we don't want them to be in that state. So we want to kind of put them together once more for the next phase. So in other words, the program is split up. The program is split up into multiple phases. Okay. And each phase will start with all the programs together. Okay. So that is what this particular style of IPC communication is all about. That's called barriers. As we can see. They move, and then we create a barrier, and they reach the barrier, and they have to wait until they all gather together, and they will be moved to the another phase. So it's a phased implementation. All right, that brings us to the end of IPC. The next one is where we'll be learning a lot of important things. Of course, important things are everywhere. A lot of important things related to scheduling. Okay? If you have any questions, feel free to ask me at this stage, because the next one, in the next part, we will focus purely on algorithm. Purely on algorithm, because you understand it's all about scheduling. So our focus will be on algorithm. Okay? Any question from this part? All right. So if you don't have questions, go ahead, study this part, and see if you have any questions. You can ask me in the next class as well. So we will quickly go through
Mommy.
the attendance. Many of you were here. We take your attendance. Wait a minute. All right, there we are. Attendance. Xuan Huang. Xuan Huang. Chi Kang.
Yes.
Vin Phuc. Vin Phuc. Duc Huang.
Yes.
Luang Ha.
Yes.
Niu Huang. Hu Huang.
Yes. Yes.
Tan Hum.
Yes.
Nafat.
Yes.
Din Min.
Yes.
Quoc Huy.
Yes.
Quoc Huy.
Yes.
YN.
Yes.
Kim Thak.
Yes.
Nhat Min.
Yes.
Tien Phuc.
Yes.
Wang Huy.
Yes.
Min Kuang.
Yes.
Du Bao.
Yes.
Quay Min.
Yes.
Lam Chuk. Okay.
Yes.
And Quoc Hum.
Yes.
All right, just a quick repeat of the folders. Vin Phuc.
Yes.
Xuan Huang.
Read.
All right, thank you and have a nice day. I will see you again on Wednesday. Yeah. Just remember, we'll get started with scheduling. So this week, scheduling actually might take 2 sessions. So at the end of this week, we're supposed to finish this chapter, process, threads, and IPC, etc. Chapter 2. All right. So bye for now, and we'll see you again on Wednesday. Bye.